In this lesson, we're going to look at additional rules above and beyond what we did in the previous section. The goal is to now tackle derivatives of products and quotients. In addition, we'll talk about higher order derivatives, which is simply the idea of taking a derivative of a derivative. Let's start out with a motivational example to say that the rule for taking the derivative of a product is not as simple as you might hope. One would hopefully say, well, I'll just take the derivative of each one and multiply them together. That does not work. Here's an example to show you this. If I take the derivatives of these two functions, the derivative of x is just 1. And the derivative of x squared is just 2x. So the derivative of these two functions is 1 times 2x, which is 2x. Now, that's the product of the derivatives. What if I take the product of the functions and then take the derivative? We get x times x squared, which if you add the exponents, you get x cubed. So the derivative of the product of the functions, the derivative of x cubed, with the power rule, we see that's 3x squared. As you can see, those are different. There is no easy rule that can calculate the derivative of a product. However, the rule that we're about to learn is not extremely difficult once you get the hang of it. This is what we call the product rule. The product rule takes the product of two functions and calculates the derivative as follows. Take the derivative of the first function and multiply it by the second function, plus take the derivative of the second function and multiply it by the first function. Now what this does is this gives you the ability to take the derivative of a product for any function whatsoever. This is the idea for the product rule. Every single time you use the product rule, you should say these words that I have, and every time I do it in this video, I'll do the same thing. When you do this, you will learn the rule without having to pay attention to this formula. This formula is not particularly helpful when you haven't done a lot of product rule problems. But if you use these words, the words will stay in your head and you will be able to continue to use it. It's the derivative of the first times the second plus the derivative of the second times the first. Always remember that phrase. We want to take the derivative of x times x squared, which is what we set up before. We're going to do the derivative of the first times the second plus the derivative of the second times the first. That's the setup. Let's calculate these derivatives. The derivative of x is 1. The derivative of x squared is 2x. And we've got this x outside. So we get x squared plus 2x squared. And sure enough, that's 3x squared. This formula appears to hold with what we know the answer has to be. It has to be the derivative of x cubed, which is 3x squared. Here's your first example of using it with something a little bit more complicated. I will mention that there is a time when you have a choice. You can either multiply everything out, or you can use the product rule. Depending on the problem, sometimes it's easier to use the product rule, sometimes it's easier to multiply it out. Let's see which one works better for us this time. So let's use the product rule first. If we use the product rule, we take the derivative of the first times the second plus the derivative of the second times the first. And there's no harm in writing out these steps. Just write out what you're saying and then try to take the derivative. Don't overcomplicate it. The derivative of x cubed minus 2x squared is 3x squared. From the last lesson, we knew that we would keep the constants in front and take the derivative of x squared. Let's start being a little bit smarter about this. When we bring the constant in front, we're going to multiply the constants. So minus 4. And the new power is subtracted by 1, so we just get x to the 1. You want to get into a habit where you can calculate these very quickly in your head. They're not hard, you just have to multiply the constants and then use the exponent you know will be there. The derivative of x minus 2, well, the derivative of x is 1, and the derivative of 2 is 0. So that just gives us a 1. Let's clean this up. Looks like we're going to need FOIL. First is 3x cubed. Outer is minus 6x squared. Inner is minus 4x squared. And last is plus 8x. Plus, the one's not going to do anything. X cubed minus 2x squared. So I get 4x cubed. There's a minus 6x squared, a minus 4x squared, and a minus 2x squared. Those all equate to a minus 12x squared. And we've still got the plus 8x. So there's the derivative based on the product rule. Let's try it from simplification. We'll have to FOIL immediately. We get x to the fourth minus 2x cubed minus 2x cubed and plus 4x squared. X to the fourth minus 4x cubed plus 4x squared is our simplified form, and we can rapidly get the derivative from here. The derivative of x to the fourth is 4x cubed. The derivative of 4x cubed, the 3 is going to come in front and make a 12. The new power is 1 less, so it's 2. The 2 is going to come in front and make it 8. And the new power is 1, so I won't write it. Notice these are the same. Now in this particular case, simplifying first was easier. A lot of times it is. But that doesn't invalidate that we need the product rule for some types of functions. Let's take a look at one of these. Here's the derivative of x squared times sine of x. Now we can't simplify this at all. So let's jump right into the product rule. We've got our first is x squared, and our second is sine x. Derivative of the first times the second plus the derivative of the second times the first. And again, I always recommend just write this down. Don't make it harder than it is. Derivative of x squared is 2x. Still have the sine x. The derivative of sine x is cosine x, and that is still times x squared. Just to rewrite this slightly, I'll say 2x sine x plus x squared cosine x. Just make sure that you write out this step when you say those words, and then worry about calculating the derivatives. That makes it a lot easier. Next example. We'll do the same thing. Your first is the square root of x. Your second is cosine x. Derivative of the first, just write it down, times the second plus the derivative of the second times the first. Now if you remember the little shortcut I gave you in the previous lesson, I told you a general rule that you should definitely learn for the square root of x. It just saves you time. By the power rule, this is equal to 1 over 2 times the square root of x. Let's use that right here. And then the derivative of cosine x is negative sine x times the square root of x. And again, I want to clean that up slightly. So the first term's fine. The next term I'll write is minus square root of x sine x. So that's using the product rule on some functions that need the product rule in order to even take a derivative. You can't simplify these. And then the last example is a derivative of the first times the second plus the derivative of the second times the first. And now let's calculate these derivatives. Derivative of x squared is 2x. Still got an e to the x. The derivative of e to the x is e to the x. And often for these problems, we finish them by factoring out the e term. So I get 2x plus x squared on the inside. The quotient rule. The quotient rule is a means to calculate the derivatives of the quotients. You've got a top function and a bottom function. The top looks very similar to that of the product rule. You've got the derivative of the top times the bottom, but then we use a minus when we do the derivative of the bottom times the top. Finally, there is a denominator here of the bottom squared. Here's the words. Again, when you do the quotient rule, say these words, at least in your head. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Let's jump right into this and do one. So if I'm going to use the quotient rule on this fraction, let's set it up as the derivative of the top times the bottom minus. Make sure you note that the quotient rule has a minus, but the product rule has a plus. The derivative of the bottom times the top, all over bottom squared. I'm just going to do one more step. We'll calculate these derivatives, and I won't simplify it any further. Often when you use the quotient rule, it's not really worth simplifying unless you need to take another derivative. It's just too much algebra. The derivative of x squared plus 4, we get 2x plus 0, so just 2x, times x cubed minus 3, minus the derivative of x cubed is 3x squared. The minus 3 is going to become 0. We have x squared plus 4, all over the denominator squared. And this is our final answer. We could simplify this a little bit, but again, it's really not worth doing. Next example, set it up. It's the derivative of the top times the bottom minus the derivative of the bottom times the top, all over bottom squared. Let's take the derivatives and leave it again this time. The derivative of the cosine function is again negative sine x, if you recall. The derivative of negative 4x cubed, the 3 comes in front and leaves negative 12. And we have x squared as our new power, times the square root of x. Derivative of the square root of x is again 1 over 2 square root of x. Good rule to know. And we get cosine x minus 4x cubed remaining. That's the numerator. And this one, it wouldn't hurt to simplify. The square root of x squared is just x. This is a pretty messy looking answer, but it is a derivative, and it can be used as such. Next one. This is an example that if you're being too trigger happy on the quotient rule, you make the problem a lot harder than it is. Note this. These are the same thing. 3x cubed over 2 is the same thing as 3 halves x cubed. So really, if I want to do y prime, I just simply keep the 3 halves in front. The derivative of x cubed is 3x squared, and I get 9 halves x squared. Done already. Didn't need the quotient rule. Same thing here. 17 over 3 can be in front, but this time I can think of this as an x to the negative 2. Let's calculate the derivative. Well, I get 17 over 3 in front. Power rule says bring the power in front and subtract 1 from the power, so let's be careful here. Negative 2 minus 1, negative 3. And then to simplify that slightly, it looks like negative 34 over 3, x to the negative 3, and I'll give that one more simplification as negative 34 over 3x cubed. This is the idea in general. If your numerator or denominator is a number, don't waste your time on the quotient rule. Rewrite it the way that I just did in some format. It's not worth your time to use the quotient rule with a number. That number is going to have derivative 0, which will knock out one of these terms entirely, and it'll just overcomplicate everything. The derivative of the trigonometric functions aside from sine and cosine. Remember the shortcut that I told you last time. Every cofunction has a negative derivative. Cotangent x becomes negative cosecant x, whereas tangent of x becomes positive secant squared x. Similarly, cosecant x has derivative negative cosecant x cotangent x, where secant x has derivative positive secant x tangent x. All of these derivatives are important to know. Here's your example. Let's find the derivative of y equals secant x over cotangent x minus 1. Again, we need the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top divided by the bottom squared. This is a little bit messy looking, but let's just follow the derivative rules and leave it alone. The derivative of secant x is right here. Secant x tangent x times cotangent x minus 1. The derivative of cotangent x is negative cosecant squared x. The derivative of 1 is 0, so I'll close my parentheses, times secant x, and we'll leave the denominator alone as cotangent x minus 1 squared. And this massive thing is what we're just going to write as the answer. Again, when it comes to the quotient rule, just write out what you have, take some derivatives, and call that your final answer. Last slide, and this will talk about the higher order derivatives a little bit. We talked about velocity in the previous section, and we said that velocity was the derivative of position. Now, if you've ever heard of how acceleration works, acceleration is a rate of change in your speed. Acceleration describes how a speed is changing. Officially, we're going to let the acceleration be the derivative of the velocity. What that means is this is a derivative of a derivative. Think about that. The velocity was the derivative of the position. The acceleration is the derivative of the velocity. So the acceleration is the derivative of the derivative. We call this a second derivative. Every time you hear the term second derivative, that's referring to the derivative of the derivative, and we often denote it f double prime of x. We can talk about a third derivative, which would be the derivative of the second derivative. It's just an idea of repeating derivatives. We call that f triple prime of x. And if we do any more than that, we usually quit using primes and start using superscript parentheses numbers to say this is a fourth derivative. So if I were to write it without the parentheses, that would mean something different. This is the notation of a fourth derivative, a fifth derivative, and so on. We call these higher order derivatives. Let's do an example. We've got the position function of a falling object on the moon. Here's your position function. S is in meters and T is in seconds. And what we want to do is find the ratio of a gravitational force to the moons. What I want to do is figure out what is the acceleration due to gravity. On the moon, the velocity that the object is falling is the first derivative. Negative 0.81 times 2t, the 0 goes away, gives me negative 1.62t. And then the second derivative is the acceleration function. T is the variable, the derivative of t is 1, we're just left with negative 1.62. Now, one of the facts you might know from physics is the acceleration due to gravity on Earth. S is in meters, so that's important. This is in meters per second squared. What you need to know is on Earth, for this problem, the acceleration due to gravity is about 9.8 meters per second squared. They want the ratio of the Earth's gravitational force to the moon's. Negative 9.8 divided by negative 1.62, which is approximately 6.04. If you've ever heard that the gravity on the moon is 1/6 of that of Earth, this is exactly where it comes from.